My name is Paul Marinescu, and this is a talk about testing services. But before going into any technical details, I want to talk about why I care about testing services and why I think it's important. And it's not just because testing finds bugs. You see, one of the reasons I like Facebook is that while it has grown and matured, it has kept parts of its original culture. What would you do if you weren't afraid is a question that you still see on the walls of some Facebook offices. And what you are encouraged to do is to approach engineering with curiosity and to try out your ideas. One of the things that I was told when I was interviewing with Facebook is that everybody needs to participate to the first hackathon that happens after they're hired. So you don't try out your ideas on paper. Code wins arguments is something that you might also hear at Facebook. You prototype, you measure, and you iterate on your idea. And this might sound simple, and it might even be simple at a small scale, but it becomes increasingly difficult as you work with more people, as you work on an increasingly large code base, and as you have a responsibility towards more and more users. But this is, I think, the best moment for the infrastructure to rise to the occasion and support the engineering culture. So let me give you a few examples. The only way to iterate fast is if the deployment system allows you to release your code often and independently of other releases. Also, the only way to iterate quickly is to have good testing. And that means a testing culture, effective testing tools, and testing frameworks. Now, also, testing is going to help you enormously when you transition from a prototype to an actual product. So, in a nutshell, I think testing gives you some degrees of freedom that you cannot otherwise obtain. And I care about testing because I care about that freedom. That being said, let's look at the technical details. And the best way to start this is by looking at Facebook's infrastructure. This is the 10,000 feet view of the infrastructure. And at this zoom level, it's pretty standard. On the left, you have the front end, code running in the browser or a mobile app. It talks typically through GraphQL to a web server. And the web server may either fetch data from storage or it may contact a backend services. The backend service is needed for situations like, say, your friend has posted something in a different language and you tap translate. A backend service is most likely responsible for making the translation. A backend service is also the place where I might go to implement my new great idea. And it's a good place because I can choose the programming language, I can choose how often to deploy my service, and I can choose how to scale my service independently of all other services. Of course, I also need to figure out how to test my service. And here I have a few options. Really, the only option is to choose how much of each to do. So there's unit testing, which checks a single unit within a service, a function, or a class, but it does not check how multiple units interact together, and it most definitely does not check how multiple services interact. Then you have integration testing that does exactly that. It takes an unmodified service or multiple services and tests them together. And finally, you have end-to-end testing, which is typically UI-driven and also focused on the UI. I consider any coverage that you get in the backend from these types of tests more of a bonus. So let's focus on unit and integration testing then. And I want to do a small experiment with you. It comes as a question. What comes to your mind when you hear Java and testing framework? I'm going to guess JUnit because it's a pretty standard, widely used unit testing framework for Java. Let's try this again. this time with Python and testing framework. I'm thinking Python unit test because it's the unit testing framework that is bundled with Python standard library. And this works for pretty much any programming language. They all have their more or less standard testing framework and best practices on using that. However, I don't think that's the case for services and integration testing. For example, what comes to mind when you hear integration testing and service-oriented architecture? I wouldn't really know what to think of. And part of it is because service-oriented architecture is this nebulous term. But it's also because any integration testing framework for services will needlessly need to know implementation details like how to run services, how to discover services, and how to route traffic between services. Long story short, there was no off-the-shelf integration testing framework that we could use, which ultimately was an opportunity for us to try out our ideas. And let me show you what we've built. The integration testing framework has two main components. One is the code framework, responsible for boilerplate and for best practices and for helping people avoid shooting themselves in the foot. On top of this, engineers build the test environment and the test harness. The execution platform hooks into the continuous integration and continuous deployment systems, and when instructed, it instantiates the test environment, runs the test harness, including the service, gets the results, and sends them back for reporting. The execution platform is a very cool piece of engineering, but that's the topic of a different presentation. I will focus on the test environment and the test harness. The idea behind the test environment is to capture a fragment of the production environment and instantiate a copy of this fragment for each test run. So let's take an example. Here we might write a test that checks that these three services work correctly together. The requirement for this test environment is to look as similar as possible to production because we want to run unmodified binaries and we want to test the same thing that we're going to later execute in the production environment. So for that reason, we decided to use the same infrastructure that we use for production environments when running test environments. One of the side effects of doing this is that we first have to rename all identifiers to avoid clashes. Think of this as a form of namespacing. We might also make a few other changes, like modifying the resource requirements of each service, because there might be less load during testing, so they won't need as many resources. After doing this, the next big question is, what do we do with the connections that cross the boundary of the test environment? And here we have a few options, and ultimately it is a matter of policy specified by the person writing the test. One option is to replace services with mocks, pretty standard. The nice thing is that we can create these mocks automatically. All services are built on top of the same testing framework, which supports reflection, which means that we can introspect it at runtime and create these mocks on the fly. Another option, which works really well for popular dependencies, is to create an in-memory version of themselves. For example, an in-memory version of this storage system. Another option, which we can use for connections that we know for sure are side effect free, is to allow them to proceed to production. And yet another option is to drop connections altogether. Once we have configured this test environment, we have to write the test harness. The test harness essentially encodes test inputs in an imperative fashion. It's pretty similar to a unit testing harness in principle. It will send requests to the services. It may change the configuration underlying the test environment, or it may inject faults. It may shut down a replica, or it may shut down one service and check that the others continue to function correctly. These checks are typically encoded as assertions. Some assertions may check the business logic of the service by looking at responses. Some may check that the service does not crash, that it does not make any invalid memory accesses, or that it contacts the right mocks in the right order. This is, in some ways, again, similar to unit testing. And this is how an integration test gets built. Part of it are automatic, part of it are manual. So naturally, the next thing that we wondered was, how far can we take this automation? Can we perhaps identify a meaningful type of tests that can be completely automated? And this is what I'm going to explore next. But to start that exploration, let's look at automatic testing in general. And Facebook is no stranger to automatic testing. We use various tools. For example, Infer on the left, very popular static analysis tool. It's open source. You can try it yourself. Essentially, it works by transforming a program or a fragment of a program into a mathematical formula. And then it reasons about the program by inspecting the formula, but never actually running the program. At the other end of the spectrum, there's fuzzing. Fuzzing runs the program over and over and over again with different inputs, looking for abnormal behavior like invalid memory accesses or other types of crashes. When looking at all this spectrum, we realize that we get the most synergy between fuzzing and our integration tests. And we also realize that we can contribute to fuzzing and make it even more automatic. And let me show you why. And for that, let me show you how typical fuzzing works. So you have your service that you want to test. The first thing that you need to do is to carve out a part of it for fuzz testing. This is typically the part that's most security sensitive. So we'll call this the test target. You also need to manually write a fuzz harness. The fuzz harness's responsibility is to take random bits and transform them into syntactically and semantically correct structures. It will then pass to the test target. Well, they have to be syntactically correct for obvious reasons, otherwise the whole thing will not compile. But they also have to be semantically correct. And the simplest example I can come up with is that a null terminated string needs to be terminated with a null character. Otherwise, it's not semantically correct. And these requirements, the semantic ones, are implicit. So there is no way to automate this. It needs to be manually done. So once all of these manual steps are done, the fuzz infrastructure takes over and runs this in a loop over and over again, looking for bugs. But the manual steps can be eliminated if we test the whole service. Let me explain why. First of all, we don't have to carve the test target anymore because we test the whole service. That one's pretty obvious. Now, we don't need the fuzz harness because, as I said before, the services are built on top of the same testing framework, which supports reflection. So that means we can enumerate all the APIs that the service implements. For each API, we can enumerate its arguments. And for each argument, we can get its type. So we can automatically shape those random bits into the right types, create the right arguments, and send them to the service. We also don't have to deal with semantic correctness, really, because all the data that is sent to a service over the network is fair game. The service needs to respect its contract, regardless of what data is being sent, and in no circumstance it is allowed to crash. So combining these two things together, we get what I call an integration fuzz test, which looks kind of like this. One thing that I want to call out explicitly is that we need to be really careful about what we do with connections that cross the test environment boundary. That's because we don't want to have random data into production data stores. One anecdote is that some time ago, we leaked monitoring data from one of these fuzz tests, and that led to real alarms triggering and people investigating, while actually there was no problem. It was all in a test environment. So what we do here is to apply the default policy of blocking all connections that go outside of the test environment. Another interesting thing that we can do when we fuzz whole services, and this goes back to the random inputs that services use. Now, random inputs are great for discovering corner cases that developers might not have even thought of, but they're not that good at creating data that has a lot of constraints. Think, for example, a request that needs a correct checksum. A random algorithm will almost virtually never create a correct checksum. What we do in this situation is to record requests sent to production instances of a service. We sanitize them and securely store them, and then use them as seeds for fuzzing. So now fuzzing starts from a valid input and just mutates it here and there. And intuitively, this leads to the discovery of deeper code paths, ultimately leading to more test coverage. We've used this for more than a year to fuzz services in the background. How this works is that we enumerate through all the services at Facebook, and without involving the service owners, we programmatically create a fuzz test and we programmatically run it. Only when we discover a bug, we file a bug report and involve the service owners. And here we have filed more than 1,000 such reports. What we've noticed in these reports is that service owners have a hard time debugging using random inputs. Often they don't know where the problem is, and sometimes they even consider the inputs to be the problem. And this is something that we have stressed, that a service needs to respect its contract regardless of the inputs. And doing this, we are changing a bit the mentality around fuzz testing and around random inputs. There are multiple directions in which we want to improve. First, we want to take more ideas from typical fuzz testing. We want to use coverage more to discover bottlenecks in our integration fuzz tests. We also want to improve isolation. When we have gone through all services at Facebook, we were actually only able to run fuzz tests for about a third of them. And the main reason we cannot run a fuzz test is because the service does not correctly run in a fully isolated environment. So we are looking at options for relaxing the isolation requirements for fuzz tests. And finally, our ultimate goal is to allow service owners to have confidence in pushing their service to production only with unit tests and integration fuzz tests. Of course, this will require more work. Thank you.